signal of a successful shot, conditional on the state of the world being that your name is Andrew Toney. Or rather, that the state of the world is that you have Andrew Toney's ability level. And then what they did was they just looked at the clustering of shots, not just for Phil Toney, but for lots of other people, everyone else on the team, to find out whether or not there really was more clustering than you would expect. Okay? So they measured the probability of making a shot conditional on just having made or missed 1, 2, or 3 shots consecutively. So if having made a bunch of shots in a row increases the probability that you're going to make your next shot, these probabilities should be different, and they're not. Okay? And then they looked at, for any player, and then they compared the number of streaks that a player has of either made or missed shots. Right? Now, if there's this systematic variation, then there should be longer streaks but fewer of them than sort of the laws of probability would predict. So they went and they took each player's underlying ability based on the frequency with which they actually make shots and predicted how often you would see clusters, okay, to see whether or not the number of clusters they actually have is different than what you would predict just using their baseline ability level, and it's not. Only one player had a pattern different from chance, and it was that they had more streaks than chance would have predicted. And then they went and they did one more thing, and they counted blocks of 4 made or missed shots to see whether the distribution differs significantly from that predicted by chance, and it doesn't. And then they did what empirical economists always do, which is they went to a bunch of seminars and listened to people poke holes in their results, and then they went and fixed all those holes. And the things that people apparently came up with was, well, maybe players change their shot selection when they're playing well and start taking safer shots, right? So maybe they make fewer overall in the game, but they don't miss as many because they're only going for layups. Or maybe their opponents actually change their defensive strategy when someone happens to have hit a few shots in a row. Now that seems odd because you'd think that if someone was doing well and people believed in the hot hand fallacy, that they would cover them more and that they would stop succeeding. This would require that you think that what happens is that when someone's doing well, people get scared and leave them alone. But what happens in economic seminars is that people just say, well, you don't know, so you got to test for it, right? If I can come up with even the loopiest story for some alternative explanation for what you came up with, then I score points in the seminar and I look smart, and you have to go and do a bunch more tests. So what did they do? The first was that they just limited it to free throw shooting among NBA players. Where the idea is if you're shooting a free throw, right, there's A, the defensive strategy is not relevant, and B, really this is a situation where we think it's highly unlikely that you change your strategy. You have a way of shooting free throws that your coach has drilled you on hundreds and thousands of times, and so we think it's less likely that you would change it if you happen to be doing well. And the results, and then they also actually conducted shooting experiments with college basketball players, and the results are the same. Okay. So apparently the hot hand phenomenon, if it exists at all, is much less prevalent than people believe, including, by the way, highly paid professionals making decisions with huge stakes, i.e. coaches, right? Oh, he's on a streak, leave him in. Oh, he's on a losing streak, get him out. Right? And if your job is on the line, which it often is as a coach, then these are big mistakes. All right. So now the clever trick that Matthew Rabin pulled off is to show that these two things actually are coming from the same place, which is this thing that he calls belief in the law of small numbers. Okay. Now there is no law of small numbers, so that's why it's in quotes. So I'm just reiterating that these two things seem to be opposite, but they both can be explained by belief in this law of small numbers. Now remember, the law of large numbers says that in a large sample of random draws, right, the proportion of different outcomes should be very close to the underlying probability of the outcomes, and that as the sample size approaches infinity, the distribution of observed outcomes will be exactly the underlying probabilities. Yeah? Everybody, you all know that. That is a mathematical fact, supported by lots of evidence. The belief in the quote-unquote law of small numbers is the false belief that in small samples, the proportions of outcomes should be closer to their true probabilities than random chance actually predicts. Okay? Now, it just turns out, if you ask a human being to write down a random sequence of outcomes, whether they be numbers, if I gave you a piece of paper and drew a box on it and said, draw dots in the box at random, you would not be able to do it. It's not something that the human brain is actually capable of doing. We do patterns. If I ask you to generate a random sequence of numbers, it's going to be a pattern of some kind. And even if it's not obviously a pattern of some kind, the way we always get it wrong is we think that random chance can't possibly be as lumpy as it actually is. The truth is that randomness is very lumpy. Okay? So if you toss a coin 25 times, you would see a lot of streaks. And if I said write down a random sequence of heads and tails, you would not include as many streaks as you would actually see from a real coin. Which suggests, right, that we have some false belief about the distribution of outcomes in small samples. Okay? Whether or not that results in the gambler's fallacy, whether it results in the gambler's fallacy or the hot hand fallacy, is going to depend upon precisely what we were talking about a minute ago, which is whether or not you actually know the underlying probabilities. Okay? If the true probabilities are known, then belief in the law of small numbers tends to generate a gambler's fallacy, like this. Right? Suppose you've got a fair coin that's come up heads 3 times in a row. So the true probability of heads and tails on the next flip are half-half. If it comes up heads, then that makes the proportions in the resulting sample 4 compared to 0, 4 to 0, 4 over 4 versus 0 over 4. And that just doesn't look like what you know the true probabilities to be. Whereas if it comes up tails, that's going to make the proportions look right? It's just that makes the small sample distribution look better. Okay? Now, Pallas is about to say that isn't, in fact, the psychological phenomenon that we think is really going on. No, you were going to say something else. An expert coin flipper who knows how to only flip heads. I don't know whether that makes the lecturer more or less qualified to teach a class in probability. That's a little scary. I think it's fair to say that a belief in professional coin flippers does not explain the gambler's fallacy. I think it's also correct that even the most skilled croupier cannot control where the ball lands on a roulette wheel. I believe that's correct. Okay, so more importantly, meaning more economically importantly, unless you happen to run a casino, when the true probabilities are unknown, the same belief can lead to the hot hand fallacy. So suppose a basketball player makes 8 out of 10 consecutive shots at some point in time, in some short period of time. The proportion of hits and misses is 4/5 to 1. The proportion of hits, this shouldn't be 2 misses. The proportions of hits and misses are 4/5, 1/5. right? So belief in the law of small numbers would lead you to have a fairly strong belief that the underlying true probabilities are 4/5 and 1/5, right? I mean, it's true that a maximum likelihood estimator would come up with those as the point estimates, but it would also come up with an extremely large 95% confidence interval around those estimates, from which an ordinary person, if they were an ordinary statistician, would be willing to draw no very strong conclusions. So the belief in the law of small numbers isn't that the maximum likelihood estimator of those probabilities would be 4/5, 1/5, but that the standard error around that estimate is way too small. Yeah? And so people really think that that's what it is. They just know. And then suppose that you then see the exact same player suddenly missing 8 shots out of 10, right? If you believe in the law of small numbers, that makes you think that the true probabilities must have changed. Okay? And so you update the wrong thing. Instead of updating your belief about how probabilities are generated, you update your belief about the player. Yes?
So we never know what the true probabilities are. Kind of like software, you can only determine tomorrow volatility by historical volatility, not true volatility.
So the reason that I'm saying that this is more important is because in economically relevant situations, it's far, far more likely that we're going to not know the true underlying probabilities. And so the mistake we're going to make is the hot hand fallacy. I mean, Modulo Palace's licentious professor, or mendacious professor, I don't know which, highly skilled professor, I think most people know the probability of a coin coming up heads. But since that's not how the value of stocks is determined, this is the more economically important point. And what we're going to do is we're going to then come up with a mathematical trick and you'll think it's a really dumb trick, but we're going to come up with a mathematical trick for jamming this false belief into a model, and then we're going to use that model to explain things, and you're going to find that even though the trick looks really dumb, it actually explains things relatively well. And you can have the next 10 minutes of the gift certificate if you want.